Yeah, he's usually.
Do you want us to make it full screen?
Oh, I'm sorry.
Hello, everyone, and welcome to session 5 of the Roman workshop happening here this week. My name is Karen Masters. I'm a professor of astronomy and physics at Haverford College, which is just down the road in Philadelphia. So we're going to get started today with the first talk, which is by Myung Gyoon Lee from Seoul National University, calling in from Seoul, where it's quite late. Are you ready to get started?
Yes, I am.
Okay. We can't see
So you see my screen.
We see your screen, but your face is very blurry on your video.
Because of the light. Sorry about that. Because of the light from the ceiling.
Okay, that's much better. We can see you now. Great. Off you go. You have 25 minutes, and so I'll interrupt you in 25 minutes. Okay, great.
Okay, thank you. Good morning, everyone. I am Myung Gyoon Lee from Seoul National University in Korea. Today, I'm going to talk about stellar populations and observational cosmology with Roman and JWST. Today, I'm going to focus in cosmology based on galaxies in the local universe. The best merits of Roman for this local cosmology is, first of all, high-resolution imaging of galaxies. So we can use resolved stars and star clusters in a galaxy. And second, the very wide field of view imaging, so we can cover large galaxies or galaxy clusters, or we can catch many small ones in a wide field at once. So from the images of galaxies to be obtained with Roman, we can derive columnar diagrams of stars and star clusters in galaxies. You can derive their age and metallicity and star formation history and metal enrichment history of multiple populations and their spatial distributions in a given galaxy. Then from this you can tell how small to large galaxies form and evolve in the history of the universe. But stellar populations also can be used as a tool. For example, you can use the luminosity of a population as a standard candle for cosmography. For example, TRGB, it will be described later, or surface rate of fluctuations, or some variable stars like a Cepheids or supernovae or whatever. In addition, you can utilize the spatial distribution of a population to trace baryon and dark matter. So today, I'm going to introduce some example science cases on the local universe. First of all, the precision cosmography of the local universe. Then one example with dark matter in the Hubble flow. Then third one will be testing lambda CDM models with the dwarf galaxies. And then origin of intracluster and halo light. And finally, globular cluster mapping of galaxy clusters. So, the first, precision cosmography of the local universe. An excellent example of current cosmography was given by the extragalactic distance ladder database and cosmic flows project led by Brent Tooley and Karatsev and Anna and their collaborators. This is the most extensive catalog of the distances to known galaxies derived with various distance indicators. However, it is far from being complete, and then there are many more galaxies, mostly with a low surface brightness, waiting to be found and measured in the local universe. So we need a precise candle to measure distances to any local galaxies. It will be the tip of the red giant branch, called as a TRGB. It is an excellent size candle for measuring any types of resolved galaxies. The high accuracy and high precisions, typically you can distances with small errors smaller than 5%. So this TRGB is the best tool for precision cosmography. Looking at this current census of TRGB distances. TRGB is the robust candle in the era of space telescope, like Hubble Space Telescope. So most of the previous distances have been measured with the HST. The number of TRGB distances with HST as of today is larger than 500. And most of them are closer than 20 megaparsec, mainly from our extragalactic distance database project, and also a small number of more distant galaxies at the distance between 20 to 30 megaparsec, which are coming from TIPSNO, our project. So this figure shows the histogram of the known galaxies with TRGB distances. As you know, in the distance range between 10 and 30 is almost empty. This spot is supposed to be filled with Roman and JWST. So precision cosmography is TRGB. Using the TRGB, you can derive distances to every local galaxies, including known and unknown, with any type in the Roman and JWST fields. If you use surface brightness fluctuations, then you can go further. And majority of them will be new, small, faint dwarf galaxies, like ultra-faint dwarfs, most of which were covered by HST. So with Roman and JWST, you can derive a precise 3D map of the local universe, which will be used for various cosmological projects. So one example is given here, dark matter in the Hubble flow. So one example is for Virgo cluster. So 2020, Kim et al. Published a paper with the title Determination of the Local Hubble Constant and Dark Matter Mass from Virgo cluster info using TRGB distances. Oops. So galaxies around the Virgo cluster are affected by the gravity of Virgo, showing infinite motion toward the Virgo. So their motion in the universe with the lambda CDM can be described, assuming a spherical shell with radius r moving radially in a cluster with mass m by this kind of simple equations. So solving these equations, you can derive a relation between Virgo-centric velocity and Virgo-centric distances like this. Here, R lot is a zero velocity radius where the cluster is separated from the Hubble flow, and the mass is given as a function of R lot and H naught. So if we have a velocity and distance of the infinite galaxies around galaxy clusters, we can determine both the value of H naught and the mass of the cluster. So for this, we need accurate distances. TRGB distances. Oops, this is strange. Sorry about this one. Here are samples of 33 galaxies with velocity and TRGB distances, which are located in front of Virgo, collected from various literatures, and two of which are from Kim et al. So the locations in the sky around Virgo, so they are located farther from the visual radius, mostly. If we, hang on here. Range. So this diagram shows a Hubble diagram. So Virgo-centric velocity versus Virgo-centric distance. The data follow these curved lines, and the solid line is a Hubble constant line for 70 or so. So the data follow show decreasing velocity toward the galaxy cluster, and around this alert position, the velocity becomes almost zero, showing the zero velocity radius. So fitting the equations to this data, we can derive the value of Hubble constant first, or like even like this, like a 66, plus with some errors. Oh, strange. This is very strange. So the value of Hubble constant derived this way is very consistent with another method, which is TRGB calibrated Taiwanese supernovae projects. So the pink region shows the collection of TRGB estimates of the Hubble constant, and also Planck values in green, and Schultz project in the right side. So totally independently derived values are constant, which is encouraging. And then you can also get the value of the zero velocity radius of about 7 megapascal or so. From this, you can derive a mass using this radius, 6 times of 10 to the 14th or so. If you compare this value with the visual mass, then they are comparable. So this confirms that the dark matter is mostly inside the visual radius, which was found previously by Karantechev and Kashpachev et al. But you are using better TRGB distance data. So with the Roman and JWST, you can derive precise TRGB distances to the infill galaxies in the direction of galaxy clusters and groups at closer than 30 megapascal. So there will be many candidates to apply this project. Then you can obtain the dark matter distribution around galaxy clusters and the value of the local Hubble constant. Oh wait, by the way, I lost my time. Okay. Am I going too fast?
You
okay.
have 10 minutes.
10 minutes, okay.
So you have another 15 minutes.
15 minutes, okay. Then third one is testing lambda system models to dwarf galaxies. Dwarf galaxies can be classified according to their luminosity or stellar mass. For example, black shows this one. Bright dwarf galaxies, the stellar mass is range 10 to 7 to 10 to 9th. And then the fainter ones, classical dwarf galaxies, and the faintest sample of dwarf galaxies are called ultra-faint dwarf galaxies, which are barely visible in the image of the previous ones. So the stellar mass range of UFDs are, as a matter of fact, smaller than those of globular clusters. So we know there is a well-known missing cellular problem, which comes from the comparison between the luminosity or mass functions derived from lambda CDM models and observations. So this has been known for long. Also, if we see the current collection of luminosity functions of classical dwarfs around many galaxies given by Carlson et al., into figures in the left side, the Milky Way side galaxies, and the right side is a little bit more massive with like small groups. So they show diversity in their luminosity functions and also large scatter. So that missing satellite problem may be related to this one. However, they covers up to only brighter than absolute magnitude of -9. But if we need to go to fainter, which are the range of ultra-faint of galaxies, the relation between stellar mass and the virial mass are uncertain for this very low mass range, as shown in the bottom corner of the left figure, and also in the right panel. You are seeing the comparison between the Milky Way dwarf galaxy mass functions, but the lowest range labeled with UFTs, they are very uncertain and little is known. But if you get a solid database for UFTs, then you can have a better understanding of the missing cellular problems. This UFT is the faintest galaxy in the universe. So they were first discovered from SDSS in 2005. So it's relatively newcomers in the realm of galaxies. So they are faintest with the lowest stellar mass, and they are also smallest galaxies, and they have the lowest metallicity. So they are considered as like a pristine relics from the early universe. And so far, they have been found mostly in the local group, mainly around the Milky Way galaxy. But these UFDs have intrinsically very low surface brightness and very small. So it is so difficult to find them beyond the local group. However, astronomers found a few beyond the local group. So in the M81 group and Centaurus A group and GC2403, 3 UFDs closer than the distance 4 megaparsec error. However, we have more. At a distance larger than 60 megaparsec, one found in Virgo cluster and another one found in Fornax. And there are no known UFTs between 4 megaparsec and 60 megaparsecs so far. But you can imagine there will be thousands of UFTs in these ranges. By the way, these UFTs may be omnipresent because star formation in these galaxies ended about 12 years ago. If reionization shut down of the star formation in these galaxies, then UFTs can be anywhere, not only around the massive galaxies. So it was shown by simulations by Rodriguez and Wimberly 2019. So Roman is an ideal tool to survey such omnipresent UFTs, if any. So I'm going to show 2 examples of distant UFTs. The Virgo cluster, this is about 2 Roman field of view, but the blue square shows the 1 HST field, so tiny. And in this tiny HST field, studied by William Serrar, Gerald found 1 classical dwarf stellar galaxy marked with a circle, but we found 1 marked by a red box, which is shown here. So you can see a small number of point sources, which is actually members of a new galaxy. So you named it as a Virgo UFT1. So looking at the first of all CMD of known dwarf galaxies and the CMD of new UFTs. So they show a very metal poor red branch. So showing that is a genuine member of the Virgo cluster with a very low metallicity. And in the case of Fornax, we took a HSC field around the bright galaxy NGC 1316, marked by the red circle, and in the red circle shows the location of new galaxies. So this shows the zoomed in view of this new galaxy. You see a small number of groupings of the stars. This is a galaxy. So UFTs can be found at the distance of Virgo and Phoenix, but we have only found one for each cluster. And their scaling relations are consistent with the known UFDs in the local group. The red ones and the yellow star, they are Virgo and Phoenix UFDs. So they are real UFDs. So, but Virgo UFD and Phoenix UFD are on the tip of the giant iceberg because there is only one UFD in huge galaxy cluster. So you can do a UFD survey of galaxy clusters and groups and fields. So from the result of stellar photometry, you can get their distances so that you can tell whether they are member of the cluster and the UFDs or not. And also you can derive the mean color corresponding to metallicity. From this, you can test lambda system paradigm with the UFD luminosity functions, and also you can test ionization quenching hypothesis with omnipresent UFDs. Then, origin of intracrustal halo light. Again, the image of the Virgo core, the 3 HST fields are marked by small boxes. And you see a diffuse light covering large fraction of the galaxy cluster, which is intracrustal light. And you can derive the CMD of the stars in Virgo at the distance of Virgo, like this. And also, you can compare those with typical elliptical galaxy M105. So 2 HST field closer to the M105 and a little bit more distant. So if you see their color distribution or metallicity distribution functions, they show two peaks, metal poor peak and then metal rich, and then it is MDF. It's very similar between intracrustal field and the outer field of elliptical galaxy M105, showing that the origin of this intracrustal light and also halo light in elliptical galaxy are similar. But all these results are based on only a few HST fields, so we need a much wider coverage. So with Roman, wide field imaging of large galaxy clusters and groups at a distance closer than 30 megapascal or so. From this, you can tell the origin of the ICL and halo light, also assemble history of galaxy clusters, as well as galaxies in each cluster. And finally, globular cluster mapping of galaxy clusters. Before JWST, the nearest galaxy cluster with intracluster GC is known is Virgo. The farthest at the ratio of 0.3, able at 2744. So this is the GC map of Virgo in the blue map. And then in the case of able 2744, from this HST image, we derive a GC map in the middle and comparing it with a gravitational lensing mass map derived from model, finding some similarity between the two. But this is only central part of the galaxy cluster, so you need a wider field imaging. With Roman, we need only one field of imaging. But finally, I'm going to also introduce JWST view of globular clusters in the massive galaxy cluster at the ratio of 0.4. So the famous image of a SPECS cluster, this beautiful image, and zooming in the central part. In the central part, we see a zillion, many small dots which are globular clusters. Also, you can see red dots in the red boxes in the left bottom corner, which is globular clusters in the lens, the background galaxies. But from this, you can derive the photometry of point sources, and then you can select globular clusters. And finding from the comparison between bright galaxy region and also intracluster region, the fraction of blue globular cluster is larger in the intracluster region than the region of a bright galaxy, showing that globular clusters in the intracluster region are mainly composed of metal poor globular clusters. Also, we can derive the number density profile, radial profiles of a globular cluster, finding two components, one in close to the brightest close galaxy component. The outer part is IgG component, and the IgG component is much larger than the brightest cluster galaxy component. And this yellow contours are numbered as a map of globular clusters. So there are some similarity and difference between image and the GC map. Also in the GC map, the blue circle shows some GC clumps without no bright galaxies, which are interesting features. You can compare also greater lensing mass model map in the left and also the contour map of GCs. They show some similarity. So GC can be a good tracer of dark matter. Also, you can compare this with the diffusal intracrustal line map given by Montes and trio, which will be probably presented in better by Mireia's talk in the next. So there is a very good similarity between GC map and also diffusal line. Also, you can compare the GC numbers map with the X-ray map. They show some differences. You can compare the radial profiles of mass from gravitational lensing map. These various lines show various models. So there are some discrepancies among models. So if you compare X-ray, also GCs, GC black line. So in the inner part, they are very similar, but the outer part, they show some differences. But at this moment, we don't know which is right. So with the JWST and Roman, you can map galaxy clusters at redshift close to 10.5 to survey globular clusters. From this, you can study, assemble history of galaxy clusters and distribution of baryon, also dark matter. So there are so many exciting cosmological projects to do with the resolved stellar populations to be provided by Roman and JWST. So some examples were presented here. So let's enjoy the golden era with Roman and JWST. Thank you for your listening.
Thank you very much for a nice talk. We have some time for questions, and we're going to alternate with in-person questions and online questions. So we start with an in-person question. Please remember to introduce yourself. Go ahead.
This is Adam Reese, and that was a very nice talk. Thank you. The question I had, you showed a calculation of doing Virgo infall to try to get cosmography. And my question was, it seemed like you were assuming Virgo as a perfect sphere, but Virgo's pretty complicated. I think it has like 3 major subclumps. And so my question is, how sensitive is a calculation like that to kind of arbitrary or different mass distributions than a perfect sphere?
At this moment, I don't know the answer. However, I can imagine that we are looking at the galaxies far from the center of the galaxy cluster. So asymmetric distribution of mass in galaxy cluster may have not significant influence on these results. But a better answer should be given from modeling.
Okay. It seems like maybe a good way forward that maybe would be relevant for Roman is that you would want your galaxies all around Virgo. It looked like they were all in one, they were all on the front side. And it seemed like if you could compare the results all around, then you would have better confidence of whether the result depends on the mass distribution.
Yes, it will be great.
At the moment, we don't have any online questions. So if there are any other questions from the room, we can take those. Oh, make Andrea run.
Hello, this is Myung Lee. Very nice talk again. So I noticed that the color magnitude diagrams for UFTs look very sparse. I remember reading there was like a Medora paper who suggested that to get a robust TRGB measurement, you would need like roughly 400 stars in the 1 magnitude bin below the TRGB. So I wanted to ask if there is a plan for accounting for the low number of stars when you measure the TRGBs with those CMDs.
You mean my plan?
Yeah, if you had a plan or a suggestion, if you were to do use those color magnitude diagrams.
Well, first of all, I don't think I have a plan because I'm fading away. But yeah. But surely we need to do tests with that regard. But here, just I'm presenting just general properties. But the test, yeah, they should be given.
Very good. Sounds like an exercise for the student.
Yeah, sounds like that.
Yeah.
All right, thank you.
Thanks very much again. We're going to move on to our next speaker. But thank you so much for joining us so late at night where you are. So.
Thank you.
I will. Oh. Not as sure. Why can't I? Oh yeah. I just do it. Sorry. There you are. Yeah.
Is it sharing?
I don't. Are we good? We're sharing? No, we're not sharing. Okay.
It's disabled.
We don't have a share button.
Yeah,
either.
the
It's
share
grayed out.
screen is disabled here.
There we go.
There we are.
Try again, John. Sorry about that.
That's all right. Let's go ahead and share that. How does that look?
Guessing it's about to pop up.
There it is.
There it is. So our next speaker is Adam Smercina, and you have 10 minutes. And
Excellent.
Way that you
Do I need a
I guess you can use one of these,
microphone?
unless you want to stand still.
Okay. Great. Okay. Hi, everyone. I'm Adam Smercina from the University of Washington. And I'm going to tell you today about a little brief overview of what I think a renaissance in our understanding of the merger histories of nearby galaxies is going to look like with Roman and JWST. There we go. Okay, so the merger histories of galaxies are really important for us to. There it is. Sorry about that. Merger histories of galaxies are really important for us to understand because we think mergers are a primary driver of galaxy evolution, right? And so to measure the merger histories of galaxies, we're typically, for nearby things, we're looking at the stellar halos of galaxies as a central prediction of lambda CDM. As galaxies merge and larger galaxies accrete smaller galaxies, they form these diffuse and structured stellar halos, like you see here from the FIRE simulation. And we spent sort of the last 10 years or so kind of combining insight from galaxy simulations like this, as well as observations from the ground and space, to really try to understand what we can extract, the information that we can extract from these stellar halo measurements. And the big thing that we've learned is that the largest merger that a galaxy has experienced in its lifetime dominates, the measurable properties of stellar halos. that you're able to measure. And so, what can we then learn about these dominant mergers from these stellar halo measurements? And the first thing that we need to know is the properties of the progenitor galaxy, and we get this from measuring the properties of the accreted stars in the halo. We also like to understand the time of the merger, so that we might understand the impact that this merger had on the central galaxy, right? And this is the kind of schematic goal of what we're trying to achieve. We've gone about this a couple different ways. So first of all, you could use kind of sparse HST fields, giving you a small window on these accreted halos, but with very precise photometry. You could also use a more wide field approach, using wide field imagers from the ground to study these stellar halos like I'm showing here, using the very most luminous evolved stellar tracers. So these red giant branch stars, I'm showing a map of them in the stellar halo of the nearby galaxy M64 from a very recent paper we put out. These are detected with the Subaru Hyper Supreme Cam. And with these kinds of techniques, you can detect these halos very well, as you can see down to very faint surface brightness limits. See this very beautiful radial merger remnant here in the stellar halo of M64. But there are some problems, right, with measuring the properties from this kind of ground-based photometry, and I want to illustrate some of these challenges by comparing to this single Hubble field that exists in this halo. So the color magnitude diagram of the stars detected with Hubble is shown over here. You can see this beautiful resolved red giant branch with these two very distinct populations. There's the disk population in red, and the blue stellar halo population to the left there. And you can distinguish these things very well. You can do a pretty decent job at estimating their metallicities and things. This color magnitude diagram over here is what happens if you translate this Hubble photometry to the depth and the filter coverage of our Subaru observations. All these grayed out things are stars that were detected in Hubble with Hubble that would not be detected with Subaru. We do detect this kind of nice, fairly nice looking blue red giant branch, but it's very hard to do kind of detailed measurements with this. You can only infer, for example, a very crude metallicity from this. And I want to point out that this is actually about the depth that we're going to get with LSST. So this is the very best, basically, that you can do from the ground. You might be able to push a little bit deeper than this, but not without a lot of pain. And so, it's very clear that space-based imaging gives you much more robust measurements of these mass and metallicity properties of these stellar halos. And so we've had to make this choice, right? Do we want the fidelity that we get with Hubble, or do we want, the wide field capability that we get from the ground? So with Roman, we no longer, or will no longer, have to choose between these two things, right? This is the first time that we're going to have access to this this high precision photometry over fields of view that are at least comparable to what we can do from the ground. And I'm showing an example here of a Roman field over top of this, brightest shell feature in this M64 halo. You can see it covers the entire thing in one go. And with only about, say, an hour of integration time per filter, you can get this lovely looking color magnitude diagram like I'm showing over here in these red and near infrared filters, where you resolve the entire evolved stellar population, the entire red giant branch, asymptotic giant branch. You can do very precise measurements of the stellar halo properties of the progenitor. And you can even reach the red clump, which is this very information-rich point of stellar evolution, where you can even calculate detailed star formation histories over this entire halo. And so an example survey might look something like this. These are 20 Roman fields in this kind of rectangular pattern here. So in two filters, again, an hour per filter per field, you can reach the red clump depth or calculate detailed star formation histories for the stellar halo populations across this entire halo out to 100 kiloparsecs or so in every direction from the central. This is something that has never, ever been possible before. You imagine there are 5 or 6 or so of these Milky Way mass galaxies at this kind of 4 megaparsec distance range. And so with a week or 2 total investment of Roman, we can, create, half dozen data sets such as this that are unmatched by anything that we've done from the ground for any galaxy really to date. We can even do pretty well for galaxies out beyond this distance, 10 megaparsecs and even greater. We may not be able to do this kind of detailed star formation history analysis over the entire halo the same way we could do with the nearer galaxies. But we can leverage the kind of ratio of different evolved stellar populations, mainly the AGB and the RGB, which are very bright in these near-infrared filters that Roman will give us access to. I'm highlighting work here from Ben Harmsen, who's a post-bac researcher at the University of Michigan in this collaboration. And he's found this very tight relationship between the ratio of these RGB to AGB stars and the quenching time of local group quiescent dwarf galaxies with very deep photometry to calibrate against. And this is relevant for stellar halos as well, because this gives you the sort of quenching time of the dominant progenitor, which tells you about when that merger occurred. And so again, we can do this out to kind of the edges of the local volume. The last thing I want to talk about is the impact that JWST is going to have on this science. And it's going to be, to summarize, a game changer for resolved stellar populations. We've heard in a few talks already. The example I want to use here is this central mosaic of the nearby galaxy, local group galaxy M33. This is a 3-band color image from a Cycle 1 proposal, PI'd by Eric Rosolovsky. We've got beautiful data of the center of this nearby galaxy. Resolve H2 regions beautifully. You can see individual bubbles here. And we've even, for the very first time, resolved the nuclear star cluster of M33, which has been an impossible task with HST. And I think this is a testament to both the resolution and the sensitivity of JWST. So to give a more quantitative example here, on the left is the color magnitude diagram that we obtained with with Hubble, the fatter HST Treasury program. This is about an hour of total exposure time. This is the center of M33 in that same region I just showed. And then on the right is the color magnitude diagram that we extract from that same region with JWST. This is only 7-minute exposure, and you can see it goes 2 magnitudes or so deeper than Hubble is able to do. Mostly this is due to the resolution of JWST being able to beat down the stellar crowding that so impacted the Hubble observations in the infrared, but also that exposure time is just so much shorter, right? And so again, this combination of resolution and sensitivity that JWST has given us is going to give us easy access to these detailed star formation histories, not just in stellar halos of galaxies, but the central disks of massive galaxies themselves, which is something that it's always been really hard for Hubble to do. It's going to be this really important anchor for these studies with Roman, particularly in these more distant galaxies where we may only have access to these kind of proxies, the AGB to RGB ratios, instead of direct star formation histories. So to summarize here, the era of wide and deep with Roman and JWST. Roman is going to give us measurements of stellar halos and the merger progenitors for those stellar halos throughout the local volume. Unprecedented sample sizes of these. Is going to be able to measure detailed star formation histories of these stellar halos across, globally, right, across the entire halo for these nearest galaxies. And it's going to give us at least the ability to calculate merger times for these dominant mergers out to 10 megaparsecs and beyond. And JWST is going to give us these deep star formation histories, not just in stellar halos, but also the central disks of these massive galaxies, which allows us to connect these mergers and the evolution of the central is going to be this important anchor for these shallower, but still very deep Roman studies. So this era of Roman and JWST combined is really going to be this unprecedented opportunity for us to understand these entire evolutionary histories of galaxies in the local volume, and something that nothing else planned is going to be able to do. Not 30-meter telescopes, not the Habitable World Observatory. Roman is really going to be unique for this. So we should do it. And I'll take questions. Thanks.
Adam. So as last time, we'll start with questions in the room if we have any.
So are there other questions? Because I have a question.
You have a
I also
question?
have the mic, so. Oh, okay. Okay, go ahead. Start with that.
Okay, we can start online and then we'll go to Andrea. That's fine.
All right, so there's a question online from Ekta Patel. It says, thanks for the nice talk. From the M33 JWST ERS program, can you say definitively whether or not M33 has a weak bar or not?
Oh, that's an interesting question. It's something I've been thinking a lot about. So I've done some work on trying to look at the possible bar signatures in M33 with the HST photometry. JWST is even better in the center. Something I haven't looked at it yet, but it's something that's definitely on our minds. You can see the photometry is much better. So yeah, it's an interesting question. Definitely something we're looking at.
So I was very impressed about your ability to study quenching, doing this small to large scale. This is fantastic. And I was wondering if you also have some AGN hosts in your source, because the quenching timescales and properties may be a little bit different.
Absolutely. I think specifically for this technique, this is going to be really powerful, because you imagine getting out to things like M106 and NGC 4258, right, which we know has an AGN. And I think understanding, the sort of quenching time or the merger time scale for the dominant merger that's responsible for these Chandra winds or whatever that we see, the X-ray winds. I think that's something you could definitely do. And if we get out beyond 10 megaparsecs, there might be other examples of galaxies that have AGN, and we can try to understand if the mergers correspond to this AGN triggering time. And I think that's, fascinating. Yeah.
Very nice. If the next speaker could come up and change over slides, well, we could have one more question if there is one while we do that. If not, let's thank Adam again. That's a very nice talk. Doesn't seem to.
Oh, I can't plug it in.
Ah, that's it. Which is yours?
Oh, I'm sorry. Yeah.
It's right there. You can get it. But we need it in.
Huh?
Stop share.
Oh, you stop sharing.
I see.
Click the button.
Can you hear me? You seem good. So our next speaker is, the next piece of paper is Nandini Hazra, who, again, you have 10 minutes. So,
Hello and good morning. I'm Nandini Hazra. I'm a PhD student at the Gran Sasso Science Institute in Italy and also at the INAF in Teramo. I work with Michele Cantiello and Marica Branchesi, and right now I've been working with John Blakesley at the NORA lab for a few months, working on my SBF procedure. Majority of my work focuses on the two distant indicators I've circled in red, and I like to start my presentations with this fairly outdated version of the extragalactic distance ladder. We've made a lot of improvements on this, so somebody should get on that and make a new graphic. It's not going to be me, I'm bad at art. Well, so the extragalactic distance ladder allows us to go from very, very local distances up to very, very far distances. And why do we care? Because having accurate distances allows us to calibrate masses, luminosities, other quantities much more accurately. And it might probably also help us resolve the Hubble tension down the line. So my work focuses on these two indicators, primarily the globular cluster luminosity functions, which is in about the tens of megaparsecs regime, and the surface brightness fluctuations method, which goes up to 100 megaparsecs, and we hope farther with newer surveys. Stuck. So the idea behind the surface brightness fluctuations method is that when a galaxy is closer to us, it looks more mottled and we can see more features in its underlying stellar populations. And the farther away it is, the more smooth this profile appears. So the idea is to sort of calibrate this spatial fluctuation and use it to calibrate distances to these galaxies. And this was done for the first time in the late 80s by John Tondry, and we've been using this method ever since. And turns out that it gives us very, very accurate individual and group distances, and individual distances as accurate up to 4%. And we really like that, because in recent years we've had very, very accurate distances for very major discoveries. For example, the GW170817 host for the dark matter-free galaxy, and for the first image of the black hole, the most accurate distances to all these three targets were calculated using SBF. And I will give a very, very short and brief overview. The SBF method is fairly complex and has not been very accessible as such to the community due to that complexity, because it involves many steps of modeling, masking, and photometry, which need to be done iteratively to get a high fidelity idea of what sources you're working with. Overall, the SBF signal is a ratio of the second to the first mode of the luminosity function. And how we get that is by modeling the galaxy profile, removing it, and characterizing the residuals very accurately. One of the major sources of error for the SBF signal comes from globular clusters. And so what this means is that the globular cluster population in these galaxies need to be characterized very, very accurately in order to get a handle of what is this underlying fluctuation that is not coming from the underlying stars, but from the globular clusters instead. And the globular clusters themselves are actually shown to have had a Gaussian-like distribution, which the turnover or the peak of this Gaussian distribution can itself be used as another distance indicator. So characterizing the globular cluster population in these galaxies gives us a handle on the galaxy evolution properties, but also the distance of itself with another separate indicator. And so this is work that we did characterizing the globular cluster luminosity function in a lenticular galaxy in Hydra 1 using HST data. Our goal in this project has been to build a pipeline with Python, so using open source tools and softwares to make SBF distance measurement more accessible to the community. We're calibrating using precursor LSST data, which is data from the hypersuprime cam of Subaru, and also using CFHT data. Our overarching endgame is to make it accessible during the operations of Rubin, when we'll have data from hundreds of thousands of galaxies. And we would like to use this pipeline also for globular cluster science, because it's an ancillary data product that comes out very naturally, and we can use it to do science. What we found in the process of doing this work is that the pipeline we have built, it extends very well to other instruments that we were not expecting it to. One example I showed you in the previous slide was the HST data, but we've also used it on JWST data, which is something that I will show you a little bit now. So here's our favorite Stephens quintet that we know and love. We've picked one galaxy, NGC 7317, in that frame, which is like right there in the magenta box. And we've picked two background frames around it to do a sort of background decontamination. We've used data from NIRCam in 3 short wavelength filters and 3 long wavelength filters. This will allow us to have wider range of colors to go and look at the globular clusters and how that looks. So the first step in doing this is to model and remove the galaxy profile. We've done this using elliptical isophotes, and we've done this in Python. Occasionally we resort to IRAF when Python does not work super well for us, but we're optimistic that we'll iron out the kinks in that. This is one of the highest overheads in terms of time in our pipeline, because the modeling takes a very, very long time to resolve. Masking and modeling is done iteratively, so as to not let the very bright objects mess with our signal. I'm going to flip back and forth between results of JWST and other instruments, just to very briefly give you a glimpse of the capabilities of how we are working with this pipeline. So we also get some intermediate calibration information from these images, such as the aperture correction and so on. And this gives us a better handle on the photometry that we are doing in the frame. We're using source extractor as a tool to do the photometry in these frames. And once we've obtained the aperture corrections and corrected for them, we can go and look at their globular clusters and try and isolate them from the rest of the objects. In this, the upper panel and the lower panel are two different bands. One is a short wavelength and one is a long wavelength from NIRCam. I would urge you not to look at the last frame on the right because I'll come to that later. So if you look at the first two frames on the left, I've characterized the globular clusters just by selecting them at this stage using their compactness. So basically separating out the very compact objects from the extended ones. I've done that using the concentration index, which is the difference in the magnitude between two bands. So this, a very tight correlation in that tells us that at different apertures, the compact object flux does not increase a lot. And I've also used the class star, which is a parameter that comes out of our photometry tool, which is an extendedness indicator. On the right, so all the sources are in golden, and the sources that I have identified to be sort of globular clusters are in purple in the first two panels on the left and middle. On the right is just showing all the sources detected in the frame. It can be a little confusing, but I'd be happy to chat about it later. So you can see that there is an overdensity closer to the center, but it's not very visible when you look at all the objects altogether. So what we do is we take only the objects that we are identifying as compact and within a certain magnitude range, and we see that there is an immediate overdensity near the galaxy, but also some scattered objects around it. When we look at the color distribution of these objects, we see that they immediately separate into two distinct blobs on the left. So the golden objects on the left are all the objects, and then the purple ones are the ones I selected using the selection criteria I showed earlier. And so the purple objects we are hoping are globular clusters. What we are seeing is that they agree very well with simple stellar population theoretical models that shows us a color range in which globular clusters should lie, and we see that they mostly lie within that blob. Well and good. We would like to also go ahead and characterize the globular cluster luminosity functions. We are seeing some interesting features, which is that globular clusters in such a galaxy would usually show some sort of bimodality, which could be a tracer of galaxy evolution or color metallicity relations. But it's unclear if we do actually see this bimodality in the NIRCam photometry. We are also characterizing the globular cluster luminosity function itself in large wavelengths, which has not been done before. And we would be obtaining a globular cluster luminosity function distance, which goes farther than has been possible so far with other instruments. Once we characterize the globular clusters and have a better handle on that, it also allows us to go ahead and characterize the SBS signal. How we do this is by comparing the power spectrum of the residuals. So when we remove the model from the image, we have the residuals, and the power spectrum of that can be matched to the power spectrum of the PSF in the image. So this is one result that we have from CFHT. We've compared, so the power spectrum of the PSF is in the lower frame, the bottom right frame, and just above it with the squiggly lines is the power spectrum of the galaxy. When we match the power spectra, what we get is a very good handle on the SBF spectrum. We are still calibrating this for HSC and for CFHT, and our future step is to go and look at this SBF signal in the JWST frames. The signal is very much there. We can see that it's much higher than in the background frames, and what we need to do is we need to go and calibrate it and make sure that we are not doing something spurious with the imaging itself. I have conspicuously not spoken about Roman, so I'm going to use my last minute to do that. As Adam said that in the talk just before me, that Roman is going to be the best of both worlds. So you don't have to choose. You can have wide area, and what used to be done with 130 pointings with HST can now be done in 130 orbits can now be done in 7 pointings using Roman. So Roman would go farther, would go wider, and would sort of be an SBF harvesting machine to get SBF distances, high accuracy in the thousands. And that has been the focus of our core community survey white paper. And I will end with that and take questions. Thank you.
That was great. That was really interesting. Do we have questions for Nandini from in the room? Okay. So please wait for the microphone and remember to say your name.
Hi, this is Adam Smercina. Just to give you a chance to talk a little bit more about Roman, there's a lot of, galaxies to choose from. So where would you point? What would you target?
So one of the ideas now is to sort of go and just look at the wide area survey without choosing where to point. But our white paper has also outlined like a larger footprint. So I don't think we have I personally don't have a very big preference. So one of the big interests in SBF is that you can go look at other campaigns, and that also gives you data within a certain distance. So I would like to look at Virgo and stuff, but yes, anyway. Yeah.
Great, thanks.
Should we just check if we have any online questions first?
Yeah, there's one question from Meet Vyas online who asks, is the Python code that was used for the simulations available publicly at GitHub or any other open source place?
So there were no simulations involved yet. We are still working on data. We hope to make the code available during the operations of Rubin. So that is our in-kind contribution for Rubin. We will have to scale it up, and we are working on that. But yes, it will eventually be available on GitHub so that you can go and get your SBF distance by yourself.
Let's have a question in the room while the next speaker gets set up. Go ahead.
Yeah, so some of the work on trying to understand the globular cluster luminosity function starts with a formation of clusters with a power law with a fairly steep slope, and then it's all destructive processes that turn it into a Gaussian. So I wonder if anybody's sort of modeled the remnants of those clusters. Are they, in some sense, another contaminant to the SBF, and has anybody tried to model that?
That is a very interesting question. I don't think so. People have modeled on what the remnants do look like, but as a contaminant to the SBF signal, I don't think so, because we assume that they've been stripped farther away where the SBF signal is so low that it doesn't really matter anymore. But yeah, that would be really interesting to look at. Thanks.
Let's thank Nandini again. And our next speaker is online, and it looks like we're all set up and ready to go. So thank you for joining us. Let me introduce Mireia Montes, who will be talking about low surface brightness universe with Roman.
Thank you very much, Karen. So hi, everybody. I would like, first of all, I would like to thank the organizers for giving me the opportunity to present today. I am quite sad of not being able to be there with you all in Baltimore, which was my previous home. So this talk is, well, somewhat or loosely based on the white paper for the Roman core community surveys that we submitted a few days ago. I hope I will be able to prove to you that the loss of brightness universe is extremely interesting and worth exploring with Roman. If you are interested, this white paper is available in the archive. But first, what are we referring to when we are speaking about the loss of brightness universe? So surveys like the Sloan Digital Sky survey have revolutionized our understanding of the universe. As an example, being a wide field survey, it enabled the study of the statistical properties of galaxies. However, this knowledge is biased towards the objects that you could observe. That means the brighter, so towards more massive objects or massive galaxies. When we are referring to the low surface brightness universe, we are talking about the universe beyond what SDSS was capable to observe. I am talking about the optical infrared wavelengths, but it might be already quite obvious, as we might be the only ones still talking about surface brightness and magnitudes per square second. So this realm encompasses many fields. For example, the study of the zodiacal light for knowing and understanding our solar system, the galactic cirrus, the dust of our own galaxy, and also faint structures around stars that can tell us about stellar evolution and mass loss processes. However, where this field has quote-unquote shown, where most of us are working on, is the extragalactic domain. In Sloan, we are missing the majority of low-mass galaxies. And at those lower masses is where we start seeing differences between the predicted and the observed number of galaxies. This difference is due perhaps to baryonic physics or stellar feedback that we are still not understanding very well, or other more exotic explanations like different dark matter flavors. So we do not only care about individual galaxies and studying their properties, but we basically need to observe them in numbers to populate the galaxy mass function. We also have the fainter structures around not so faint galaxies, what we call the stellar halos. In simulations, we see that as we go fainter and fainter, we start seeing a plethora of structure that shows up around galaxies. But by studying the amount of light in these stellar halos and the properties and the shapes of the structures within them, we can explore the low mass end of the galaxy mass function, like what I was talking before, as well as the processes that shape the halo. So in this case, observations have taken a little bit longer to catch up with what we see in simulations, but we are starting to explore more and more of these faint structures around galaxies. And of course, if we are talking about the stellar halos, we have to talk about the most massive stellar halos that are, what we call intracluster light, or ICL. Intracluster light, or ICL, are stars that are not bound to any particular galaxy, but float around following the potential of the cluster. This light is the byproduct of the interactions between the galaxies in the cluster, so it contains the information of the things that have happened during the history of assembly of the cluster. So this light is a powerful tool for understanding the formation and evolution of galaxy clusters. And not only that, this light has been shown to be an excellent luminous tracer of the dark matter distribution in clusters of galaxies. So it sort of provides a picture of how dark matter distributes in these clusters. And how dark matter distributes in clusters of galaxies is a consequence of the nature of the dark matter. Therefore, the intercluster light can also be a powerful tool for understanding dark matter. So this is the low surface brightness universe that we can explore with Roman. Low surface brightness galaxies, stellar halos, and intercluster light. I hope I have convinced, although it was a little bit rushed, but I hope I have convinced you of the interest in doing so, in exploring this low surface brightness universe. The problem is that to explore all of this, we need very deep observations. And that comes at the cost of the objects that we can explore. So we have only been able to explore the tip of the iceberg of what this regime can give us. That is what Roman comes into play, specifically the high latitude wide area survey. But most of the things that I'm gonna say applies to any Roman observation that is deep enough. The high latitude wide area survey will provide a very deep infrared view with HST-like resolution. Exploring the infrared is very important in this regime, as we cannot get a spectroscopy, and it might be that we might not be able to get ever a spectroscopy of these objects. So to study the stellar population, it's very important to have also the infrared view. The spatial resolution is very important to minimize contamination and blending, also adding the capability to resolve halo stars up to the Virgo distances, and also study globular clusters, as we have seen in previous talks. So this survey will be a game changer for studying the loss of brightness universe, even allowing to explore it not so locally as till what we've been doing before, but also at higher redshifts, and see how it evolves with time. And very importantly, it will be around 2,000 square degrees, providing the area and therefore the numbers that we so desperately need. So, in order to show you what Roman will be capable to do, and I will now talk about the study that we published last year, exploring the intracluster light in the first images release of the JWST. So I think that all of you know about this image, but this is the clusters max 0723, a massive cluster at redshift 0.4. So thanks to the infrared view and the resolution of JWST, we have seen an unprecedented view of the ICL of this cluster. As you can see here, we have been able to see all this structure, the plumes in the center, these tidal streams in the more outer parts of the cluster, that we haven't been able to see before. So to do that, to explore the intercluster light, we had to do some image processing in order to take full advantage of the images, which I think my colleague Alejandro Borlaff will take in more detail in a second. So, given that we have also multi-wavelength coverage of the cluster, we constructed the color profiles of the cluster from the inner parts to up to around 300 kiloparsecs. So, what we can see is that in the inner parts, we have that the process sending stars to the intracluster light is a major merger, as you can see here by the plumes that in the image, and also by the flat gradient in the colors. The major mergers is a 1, 2, 3 major merger of the BCG, or the brightest cluster galaxy, with this companion, and I hope that you can see my cursor here. So, and this is what happens in the inner parts. But in the outer parts, what it seems that is creating or forming the intercluster light in this cluster are the tidal stripping of satellites of a mass similar to the Milky Way. As you can see here, this is what we call the giant west loop. But also you can see here in the eastern part of the cluster with this and this tidal tails. These tidal streams, sorry. So, in summary, with JWST, we've been able to see the diversity of processes that are building the intracluster light. But of course, it's just only a cluster, so we need Roman in order to explore more and more clusters. So, I leave you with the QR code for the white paper. And if you take anything from this talk, I hope that is that the loss of brightness universe is an important piece to understand how galaxies form and evolve. Thank you very much.
Thank you very much, Mireia. We have some time for questions. We'll start in the room. Do we have any? Are there any online questions, John? There are not currently. Oh. Okay. All right. Well, maybe we're ready to hear from Alejandro. Oh, no.
That works. Well, I'll try to. Did it work? Okay. This one. Okay, first. Sorry. Just a finish. Okay. I think if you do that. Oops. Oh, look. I'm sorry.
Our next speaker is Alejandro Borlaff, still on low surface brightness scale.
Oh, well, thank you. Well, my name is Alex. I'm from NASA Ames. Today I would like to talk about the low super brightness universe with HST, Euclid, and Roman. And does it work? I make it. Okay. So ever since the very, very first simulations in the 70s, at Tumbre, we know that the remains of the hierarchical accretion of the universe are in the very low and dark regions around the largest galaxies that we see, and that extends to the more recent simulations, including two magnetic fields that depend on the parameters of the lambda CDM cosmology. But where are these things? Because when we look at the data, this is SDSS. For example, this galaxy, which is C1382, appears to be a boring, red and dead galaxy, nothing very special. And then this is a magnitude of 26.5 magnitudes per square second. So when we push a little bit farther, 1.5 magnitudes deeper, we see that this galaxy is in fact one of the largest surface brightness galaxies ever, that extending spiral disk of 80 kiloparsec. So there is a great deal of morphology that we don't know that's at the very low end. Even galaxies like this one, that's apparently an ultra-thin isolated galaxy. This is the work of one of my students, a beautiful needle in the 73. Presents, believe it or not, there is a warp in that region, and there is one of the possible responsibles of this satellite galaxy in pulling the material from the outskirts to the north in this image. So, like Mireia just said, we are only seeing the tip of this beautiful iceberg, and magnitudes of, just put some scale, magnitude of 27, where the SDSS ends, we are starting to see the signs of the low super brightness galaxies and ultra-diffuse galaxies, magnitudes of 28, the stellar streams, tidal tails, magnitudes of 29, the intercluster light, picking up some signal, the inner and outer stellar halos, and maybe someday when we break the 30 magnitudes per square second limit, we will be able to see the remains of the cosmic web. Thanks to Mireia again, I don't need to introduce this beautiful image, but what I would like to focus is in the low super brightness details of this. This is extremely valuable because we know now that this whole cluster was shallowing galaxies the size of the Milky Way, but there is a great effort in trying to extract this information from the real images, because we have lots of gradients and systematic effects that make separating this signal from the real signal from the systematic effects extremely, extremely hard. And this is something that took a titanic effort by Mireia, Montes, and Nacho Trujillo to get this image corrected in a way that we could use it for doing science. The problem is that by applying all these corrections over the images, we are losing a lot of information from the ultimate potential of the images. The theoretical limit of these images will be about 31.2 magnitudes per square second in boxes of 10 by 10 seconds. That depends on the size of the structure that you want to detect. So it's a little bit of wobbling here. But due to these gradients, the limit of this, the scientific results on this paper is at 28. That's bad. That's really bad, because that means that we are losing all this interesting part where exactly Roman is going to be picking up a huge advantage. Roman will be able to, in theory, will be able to detect in 10 minutes structures of 29, 30 magnitudes per square second in 10 by 10 arcseconds and boxes, and in 30 minutes reach to the 31 magnitudes per square second limit. So we need to get this done. Now, where these gradients are coming from? Some of the gradients come by the flat field, and this is a little bit trick from photometry. If you take photography, sorry, if you imagine that you are in your holidays and you want to take a picture of your favorite museum and there's a bunch of tourists annoying, moving around, and you don't want to be in your picture, you can take many images and average them, and they are gone. So this is called sky flat filling, and we demonstrated that it works using the zodiacal light as the background to retrieve the flat field from the image without using for the large scale, without using internal calibration units. We can introduce gradients for the large scales. But that's only one part. The other part is straight light. Straight light is great for RT pictures, but horrible for astronomy. And we need to get rid of it. And it's really hard because it depends on the photometry and the position of the sources that are around the field of view and inside the field of view. This is one image from HST that I really like. We're showing Titan and Saturn, and you can see the straight light from Saturn getting inside the field of view. And this is the PSF, but this is different. This is the NDI. The normalized detector ranges measure how good is your telescope in blocking the light that goes outside the field of view. And if you know it, if you know this function, which is a 435 parameter function depending on the degree and the wavelength and everything, in theory, you should be able to model and correct the straight line gradients, including ghosts, everything. So we need to do that. Now, why we need to do that? Because this is all for correcting the sky background. The problem is that you can measure the sky background on the images themselves, but that doesn't work for things that are very large. If you have a large object in a systematic gradient, and the gradient is the order of the size of the thing that you want to detect, and you measure the sky background in these images, you're going to include the parts of this galaxy in the background model, and you end up with an image which is over-subtracted. And this is the sad reality of many observations in the Hubble archive. This is from the class survey, and you can see how there is a background of negative counts around this extended galaxy cluster where the intercluster light should be. So this is something that we need to correct. Without using the straight light correction and only using better masking and more careful sky background subtraction, we were able to demonstrate that the Hubble ultra deep field still retain huge amount of light that had to be recovered, and you can see the limiting size in the 29 isophone magnitude as a function of the version of the image. This is the extreme deep field and the ultra deep field, and this is our version, and you can see how the galaxy is twice the size using the same data, using the same observational data. But this is suboptimal. Ideally, we would like to know exactly how bright is the zodiacal light, which is at 22 magnitudes per square second, model, remove it. Then how bright are these stars, where they are, where is the emission from the sun, the moon, the earth, remove it, and then get to the galaxy or whatever that we want to detect in the field. And for that, we need the normalized detector irradiance. And this is exactly what we are doing for HST. In a project that was selected in last year, a Hubble Archival Research Project called StriKOR. The idea is to reconstruct the normalized detector irradiance for this very complicated setup, because for Roman it will be far easier. We will have the Earth super close to us. But if we succeed, we will be able to model and correct all these gradients created by the Earth, Moon, the stars, and generate as a product straight light background models that will help you to create better sky background correction in your images. We are starting by using the zodiacal light, improving models by Sarah Caddy and the rest of the team in SkySurf in Australia. Generating, this is not at the same scale, but I had to exaggerate a little bit the gradient from the zodiacal light background. But you can see that we are, without using the image, we are able to generate the background of the zodiacal light in this galaxy. And we are using extreme observations from HST. This is very close to the Sirius star, to model the NDI and the amount of light that we receive from this object as a function of how separated are we from the large object from the field view. We model, and we hope that we will be able to demonstrate that this works in Euclid using the piece detector. We were able to, and the NDI provided by the engineering team, to generate models that provide you how is this gradient pixel to pixel for the 36 detectors of the piece detector. But the idea would be to apply this to Roman, and because we had very large field of view compared to JWST and HST, very interesting extension in the spectral range. So the idea would be to apply all this and get all this ready before the Roman launches in this project called Rosalia, Roman Sky Analysis for those who have brightness imaging and astronomy. Hopefully will be selected for the Roman Roses proposal. And I would like to finish with this image from the SDSS and the 7331 Galaxy and the Stefan Quintet here. You can see here some straight line gradient, which limits the signal to noise that we get in this image. But if we push a little bit further, this is how the universe will look like if we apply all these techniques and make a more bigger effort to retrieve things that are a bit larger than a galaxy at redshift 7. So, these are my conclusions. Well, thank you very much.
Very much. Those beautiful images to end on. Oh, looks like we immediately have a question in the room. Great.
Hi, Kara Gilbert. Very nice talk. So my question is, so, you're getting ready for the model to do this with Roman. I assume you will need some on, sky observations to calibrate it. Will you be able to do self-calibrations, do you think, with the survey data that will be taken anyway, or do you think you'll need to do specific pointed observations to calibrate it?
That's a very good question. When we did this project for Euclid, one of the conditions was that we couldn't move the telescope at all. Like you had to use the science data and the survey because that's not movable. So we all these techniques that we developed for generating the straight line modeling and measuring this on orbit, it's based on the assumption that we won't be able to use anything else than the surveys. But if we are able to point our telescope and rotate it around a bright object and probably use the moon to measure this on orbit, that would be absolutely great. One other idea is that if this flat field correction depends on how bright the solar light is. And by definition, you always want to point to the regions where the solar light is less bright. So if for calibration, it would be fantastic to have a program to point this to a very bright part of the sky and the solar light and use it as a dome. We cannot have a dome, but we can have the solar light, which is sufficiently flat for doing this. So yeah, it will be very important.
Very nice. Do we have any more questions in the room? We don't have anything online. I'm going to switch over to the next speaker, though.
Hi, this is Smercina. Really nice talk. Thank you. I apologize if I missed this, but what makes Roman so much better at this low surface brightness science than, for example, you showed with JWST and SMACS?
It's the field of view. The problem is that this gets harder and harder and harder when you get a field of view which is narrow. Because, for example, imagine that you try to point your HST was point to Andromeda, and you have diffuse emission, but you don't know where your zero is. But if you have a very large field of view, you can call a pixel a zero.
I see.
It's way easier when you get a large field of view. That makes all these errors, all these hazards and uncertainty, so it's way better to use that as a reference. So Roman is absolutely fantastic.
I see. Thank you.
So our next speaker should be online. I don't know if I see them.
Yes, I'm here. Sorry.
Here. Okay, great.
Yes, I'm here. Sorry about that. I'll just try to share my screen first. Just give me 1 second.
And if it's possible to have webcam, that would be nice.
I'll try. Let's see. My camera's not been like functioning properly, but I think you can see me, right? Yes.
Yes, we can see you.
Okay, perfect. So let's see if I could. All right. Can you guys see my screen?
Looks like we're good to go. So you should have 10 minutes, and I'll interrupt you at 10 minutes.
All right.
Yes.
Perfect. Thank you very much.
Yes, this is Mainak Singha, who's going to talk about AGN in green galaxies.
All right. Hi, everyone. It's Mainak Singha from NASA Goddard, and today we'll be talking about a search for AGN in green peas in the local universe. So just to start with, like, what are green pea galaxies? So like green peas are like extreme emission line galaxies, like relatively seen at like about like redshift about 0.3. Like due to like their extreme emission due to their extreme emission line properties, and like especially the O3, they are usually seen as like green, and like their sizes are like about 0.3 kiloparsec, and which is the reason they appear as like peas are unresolved by SDSS. This is the reason they've been like called as the green pea galaxies. But these galaxies are like incredibly important to understand the reionization of the universe, because they share like so many similarities with their high redshift Lyman alpha emitters. Their compact sizes are very, very similar to like what you find at redshift 8, about like 8 and 9. Like recent studies by like Rose et al. Found that the sizes, the half-life radius of these green peas are exactly similar to like what you find at like the epoch of reionization of the universe. Not only that, they basically span the similar metallicity range, and their optical spectra are totally identical. So as if these green pea galaxies are like a living fossil from the era of reionization. So it's really important to study them, because like they are basically give us the high redshift information at such a low redshift. But now the question comes in, like, what drives the reionization? Like, that's been like a totally long-standing debate. In 2015, Maddow and Hart wrote a beautiful paper, and they suggested that if there are like sufficient amount of low luminosity AGN about redshift 4 to 6, those AGN can mostly dominate the reionization energy budget, and with like very little contribution from the star-forming galaxies. So that's interesting, because it's usually hypothesized that the low dwarf star-forming galaxies are the main reason for the reionization. Obviously, there are many people who have suggested that like a massive galaxy such over like into 8 solar mass, they might drive the reionization. So there's like a whole lot of controversy going on between like what's the main cause of the reionization. So we really want to find out if there is like AGN, if there's any role of AGN in the reionization. So there's a recent paper by Hurricane et al. 2023 who used JWST near spec, and you see in the model that in the central panel that they have found like a broad line region, which is like a classical signature of AGN. So on the lower panel, I'm showing you a unified AGN model suggested by Ori and Padovani, and the broad line region is usually hidden by the torus. For like type 2 AGN, for type 1 AGN, it's not hidden by the torus, and then you get to see it. And when we're seeing such broad emission line region in spectra, and that's basically giving you an indication that, well, we have AGN there. Now, this is not like a low redshift galaxies. You're finding at like redshift 4 to 7, and that's basically the similar redshift range Maddow and Hart predicted. And Hurricane et al. Also added that this AGN could provide up to like 50% of the ionizing photons in the reionization budget, which means that like there may be a significant AGN contribution in the reionization process. So it's crucial to understand like what's AGN doing there. Now, what's the relation between AGN and green peas? If you look at the right panel, I've shaded the region where green peas usually lie in the BPT diagram. So now the AGN host galaxies from the Hurricane sample and the green pea galaxies are sharing the very similar space in the BPT diagram. Not only that, a study by Harish et al. In 2022 has suggested that green pea galaxies could also have AGN. So it's really worth to study any possible evidence of AGN to understand what's going on in the reionization process, or if there's any AGN contribution in the reionization process. And that's why we really want to find out if there's any AGN in green peas. So what do? We look for the Chandra data archive, and we found that there are only 4 green peas with detectable X-ray emission in the Chandra ACES. But we also found 2 other green peas which show mid-infrared variability in mid-infrared variability. So I'm showing you like one of those in the top right panel. There you can see there's like obviously the light curve is obviously changing, suggesting that there's an AGN, because AGN are basically thought to be variable across the electromagnetic spectrum. But for the same source, you don't see any optical variability. So you see mid-infrared variability, but like no optical variability. So what does it suggest? If there's an AGN, that's optically obscured. So we may extrapolate that, and this is like not for like one source, that's for like about like many sources. So we may extrapolate that to a conclusion that green peas might harbor optically obscured AGN. Now we have another line of evidence. So what do we find? We made like a wise color diagram, and we find that the 6 green peas are basically falling in a region which is coincident with quasars and Eulers. Eulers have been thought to harbor active black nuclei, and there are like numerous JWST papers and other on the optical infrared in every wavelength. We have seen like the presence of AGN in those galaxies. Now, starburst galaxies could cause this kind of mid-infrared colors, but the problem is that they need to have really high ionization parameters. And for the green peas, you're seeing that the ionization parameter is much lower than starburst galaxies need to have to produce these mid-infrared colors. So therefore, basically the common conclusion would be the mid-infrared color is not due to any stellar feedback processes. It may be much more powerful source, such as an AGN. Now, looking into the X-ray data, we find something really interesting. The observed X-ray luminosity you see on the top left panel, it's about 6 times higher than one would expect from their X-ray binary contribution. So in the X-ray binary, we're taking the contributions for the low mass and the high mass X-ray binaries. And if we add them together and still see that we are having like a much more X-ray emission than could be explained by just those 2. So, okay, there's like X-ray binaries are thought to be the major contributor in the X-ray emission, but like they are not. So where's the rest of the X-ray emissions coming from? So there has to be a much more powerful source, aka maybe a massive black hole. So not only that, if we go into the optical data, sorry, I'm just trying to kind of move this one around. We find that the number of photons that you need to produce the helium-2 emission just cannot be explained by the XRB contribution. So why we've been talking about that? Because in X-ray binaries, the companion stars are like Wolf-Rayet stars. whose classical signature is having like a prominent helium-2 emission. Now, the Wolf-Rayet stars may drive the helium-2 emission, but the contribution we'd expect from the XRB or Wolf-Rayet star cannot just fully explain the helium-2 emission we're seeing here. So there has to be some other contribution. And not only that, in the helium-2 spectra, for Wolf-Rayet stars, one would expect the spectra to be, the helium-2 spectra to be broadened, but like this helium-2 lines are like much narrow, and their kinematics is about velocity dispersion is less than 100 kilometers per second. And that's basically what we see in the AGN narrowline region. And not only that, we are also seeing that we find there's like no C4 carbon 45808. That's like a classic Wolf-Rayet signature. And like all these dots just only lead towards the conclusion that maybe it's not the stellar feedback process that's causing all this line of evidences. There has to be a massive black hole. But we want to be a bit more cautious here, because for the X-ray emission, it's just not XRB. Recent study by Osnikova and Scherer have suggested that the winds from superstar cluster and superbubbles could also generate X-ray emission, and that actually surpasses the XRB contribution by a factor of 2.
However, that's 10 minutes.
Sure, perfect. So what we did was we really wanted to find the maximum amount of contribution the stars could cause. So we just added the XRB contribution and the stellar winds. So if you remember from the previous slides, the observed X-ray luminosity is about like 6 times down the XRB, and the stellar wind contribution is like 2 times the XRB. So if you add them together, you're seeing that the observed X-ray luminosity is just about twice about the XRB plus wind. So like basically that twice of the stellar contribution. So in other words, the stars only contribute 50% of the observed X-ray emission. So where does the other 50% comes from? There has to be another non-stellar source that has to be powerful enough to like give rise to all those immediate infrared colors, create all those spectra, and therefore the most reasonable conclusion was there has to be an active galactic nuclei which is doing all these. So what if there's an active galactic nuclei? What's the mechanical output? To understand that, we used the hydrodynamic simulations by Gaspari and Sadowski 2017, who suggested that in AGN feedback, the mechanical energy output is basically similar to the X-ray luminosity of the AGN. So for our samples, the X-ray luminosity is about 10 to the 39 to 10 to the 40 arcs per second. So that has to be the mechanical energy output from the AGN in Greenpeace, if they do exist. So obviously there has to be a caveat that we really need to, we probably need like even more stringent evidence to make like a major conclusion. But all these line of evidence is just suggesting that like there's this not just stars, you need something else to make to connect all these dots. So that's the reason we're trying to find Greenpeace is not only just in the 6th sample, but we need like a much larger size to actually use the test to make like a much more stronger conclusion. And that is where Roman comes from, Roman shines. So Roman has this huge field of view of about like 0.26 square degrees, and it can actually utilize the near infrared wavelength range to trace all the helium-2 emission lines, H-alpha, that getting the star to trace the star formation, O3 to take the equivalent width to find out if those are like green peas or not. And we can actually probe like millions of green peas from redshift 0.3 to 0.24. So in this redshift range, we can actually find out like what's happening from the end of the cosmic dawn to like the present days, and like how are like green peas behaving, and like what's based and what's the contributor of the reionization of the universe. Like Greenpeace can give us so much information. And thanks to Roman, we will be able to like get like so much more statistics than like Hubble and JWST was ever able to find. Because,
thanks so much, Mainak. I think I need to cut you off there. We're on time. So we might have time for a very quick question while the next speaker gets set up. Yes.
So I guess a quick question then from me. Yes, no, sorry. So have you looked at radio variability? Or just stacking in the radio?
Yes, so basically what we're trying to do was to apply for like a Merlin observations, but there are some radio data for Greenpeace. So that's our next goal, to look into the radio observations and see like what's going on. So obviously that's like a next thing to do.
All right. All right, I know I'm the last talk before lunch, so why don't I start? Yes, beautiful. I'm a bit of a departure from the rest of the session, but it's been a wonderfully interesting session, so I'm happy to be part of it, but I'll be talking about probing cosmic noon with what is now a soon-to-start survey with the prime focus spectrograph, which we just got commissioning data with the near-infrared arm just a month or two ago, so I'm hopeful that we will actually start the survey in 2024. And you can see that we're a very wide area spectrograph, which is nicely complementary to the area of Roman. What you need to know is a 1.4 degree diameter field of view with 2,400 fibers, each about an arc second. We cover 3,800 angstroms to 1.26 microns, and so this is a really massively multiplexed spectrograph that should be very powerful for galaxy evolution, particularly around cosmic noon, where historically there's been a redshift desert. So PFS will have three main science pillars: a BAO survey out to redshift 2 or so with O2 emitters, a near-field cosmology survey of both local group dwarfs and the halo of the Milky Way in Andromeda, and the galaxy evolution survey that I'll be talking about. And there's lots of themes that I think are well aligned with the goals of the high latitude survey. And really, this is just an extended infomercial for PFS. We want to make sure the community knows this is coming, and we'd love to promote the idea that the high latitude survey includes the PFS fields. Okay, now we're not advancing. Oh, there we go. So we will be in 3 of the 4 Hyper Supreme Camera deep, SSP deep fields, XMM-LSS, Deep 2-3, and Cosmos, where we have worked extremely hard, the collaboration over the past few years, to have uniform J-band to 23.5. So we'll be, sorry, we're having, okay. And so we'll be selecting to J-band of around 23rd, and this is because the 4,000 angstrom break is in the J-band at redshift 2. So it's about, let me just advance. Yeah, so this is a nice one-slide summary of the PFS GE survey. We're looking to get about 250,000 galaxies at redshift 1.5 to 2. We're looking to do an IGM tomography survey of about 43,000 galaxies. To the background, galaxies will probe the IGM at a redshift of 2, and then something like 14,000 dropouts and LAEs at redshifts above 5 or so. And so we really span a wide redshift range. With our wide spectral coverage, we expect to be able to probe both environments, because we're covering 15 square degrees, and also detailed physical properties of these galaxies at all redshifts. This is our attempt to find the parameter space where PFS really shines. So this is spectral resolution adopted from Natasha Forster-Schreiber's nice review versus the number of objects. And you see we live in a really nice corner of parameter space where, again, rich astrophysics and lots of objects. So what would be super great is to also have the imaging and GRISM data in these fields from Roman, because there's just a lot more science that we can do, extending H-alpha out to the edge of our continuum selected sample. We will provide rest near UV, and Roman provides the H-alpha. Of course, also we're excited about having detailed morphologies for the galaxies in PFS. HSC is amazing and has been said multiple times, probably the best you can do from the ground until LSST, but we won't be able to resolve most of the PFS galaxies with the HSC data, although it's great for selection. We can do that with Roman in the res frame optical. Lots of good science to do. One example would be intrinsic alignments. And just thinking about ways that our spectral coverage is interestingly complementary. Those are example expected PFS spectral stacks, just to give you a visual impression of all of the important lines that we're covering over these redshifts ranges. So we will have an H-alpha sample out to redshift 0.9, and then hopefully that can help calibrate the GRISM decomposition of H-alpha and nitrogen-2. And then again, we provide all the near UV lines, and Roman could give us H-alpha, which would be super exciting over these fields. And finally, there's also a lot of interest in the PFS group and reionization. So we have narrowband surveys already in the HSC deep field, and we will be following those up really to look at the morphologies of Lyman alpha to try and understand the topology of reionization. You can't really do this with low resolution spectra because you're really interested in red and blue wings and all the fun stuff that Lyman alpha does when it tries to escape. So this would be another really nice synergy. And so that's the short pitch for why it would be really a nice thing for the community to have HLS quality data in the PFS deep fields. I'm now going to take 1 or 2 more minutes to promote 2 other science things I'm excited about. One, we've heard a lot about SBF today, so I don't have to explain, but my student Gyoon Lee is thinking hard about SBF 4-dwarf galaxies with Roman. This, you saw Scott Carlston's thesis, the luminosity functions that we did with ELVs. We imagine we could get all the way out to about 70 megaparsecs with SBF 4-dwarfs. The trick, of course, is that the near-infrared stellar populations are much more luminous, so that allows you to get further out than you can do with the optical, but you need to be able to calibrate them, and you know these AGB stars are tricksy. So the idea that Gyoon is exploring is if you have LSST colors and Roman colors, can you get a tight SBF correlation? So please check out his poster. It looks at the numbers that we could hope to get and some promising looks at stellar population models that we could really do this. The other thing I wanted to talk about now, going to the opposite redshift regime, is this work we've been doing with Uncover to look for the moderate luminosity AGN at redshift above 4. We've also heard quite a bit about this yesterday from Junyi and Yuichi Harakane. We got interested because we had this lensed little red dot that Lucas Furtok published this year. It's so compact and so lensed that we can put a 30 parsec size limit on it. It's very red in the rest frame optical. It's at redshift 7. And so it's one of the reddest things in the Uncover field. And the other reason we got excited is that Dale Kochevsky published this beautiful broad H-alpha for objects very similar in Sears. So Guillermo Barro has looked at their SEDs. So you can see there's some UV light, but then just incredibly red in the rest frame optical. We also have deep ALMA. So at 1.2 millimeters, they're not detected. While you can fit the SEDs with dusty star formation in the rest optical, we think that's probably not the best explanation because we do not see them in ALMA. So we do think these are moderate luminosity AGN. This is the luminosity function from Fresco. So this is Jorit Matthey and collaborators. They actually have broad H-alpha from GRISM data. And so you can see the UV luminosity function flattens and our little red dots live here. So they seem to be the missing moderate luminosity AGN population that are just too faint in the UV. And the question is, we would love to exploit wider areas to find larger numbers of these, but they're dusty and they're not UV bright. So is there a clever way that we can use Roman to find them? And I just want to say that there were hints already from Spitzer. This is a paper by Mark Lacey, sorry for the Zoom issues, showing that this type 1, red and type 1 population, their number densities are rising actually as you go to redshift 3. It's just that with JWST, we're basically falling over these things. So anyway, that's an interesting question, and I will just leave you with the beautiful PFS footprint and take questions.
For a very nice talk, as usual. Do we have questions?
Did I go too fast?
Looks like Andre has a question.
Oh, no.
No? Okay. Adam has a question.
Hi, Adam Smercina. I wanted to go back to that slide where you were talking about calibrating the SBF and the resolved stellar populations. Just real quick. Yeah, and so that it's kind of obscured by the Zoom thing, I guess. But the overlap region, I'm assuming you're targeting the stellar mass axis is sort of set by galaxies themselves, and I wondered if
not getting better than about 10 to the 7. We have to detect them in LSST.
Yeah, right. And I wondered if the sort of stellar halos, nearby stellar halos, close to the disk where there, things aren't crowded, but are maybe there, you're getting more stars, might be an interesting target to add to this as well, to this calibration region.
Absolutely, yeah. No, we really were just focused on dwarfs, but I think there's quite a lot of science to do in the semi-resolved regime.
Yeah,
for sure.
Interesting. Thank you.
I mean, it's really one of the things we're excited about really digging into is how much information about the stellar populations can we get as well.
Right. Thanks a lot.
We don't currently have any online questions, so
I'm very excited about your red dots, and have a question about do we have masses for the black holes?
So
and the hosts.
Dale's objects are around 10 to the 7, and that's true for the Mathy objects as well. So they're sort of 2,000 kilometers, and Harakane too. Yuichi's objects are similar, 10 to the 7 to 10 to the 8. Our luminosities, if you kind of de-redden, are also consistent with 10 to 7 to 10 to the 9 solar mass AGN at 10% Eddington. There's one super exciting source that's magnified, we think very, very magnified. That's bolometric luminosity would be below 10 to the 43. So I'm super excited to see this. I should say, Uncover just submitted our masks. We're getting MSA spectra at end of July, so we should get redshifts for all of these soon. And then we'll see. But one thing, so I said they were very compact, but a thing that's exciting for us to do once we have redshifts is black hole to galaxy ratios. It's very hard to find the galaxy here, except a little bit in the UV sometimes.
What if you stack? You put them all together.
Oh, I don't know. I think we are moving into a regime where the black hole mass is more than 10% of the mass of the galaxy, because this is JWST and they're really compact. Yeah.
Looks like we have a question in the front.
So back to the PFS. So for the IGM tomography map, I'm wondering if you want to combine that with lensing from Roman. Is there anything different you do with Roman than the high latitude wide area survey, or is that?
Can you do lensing at redshift 2?
Well, that's sort of why I'm asking the question.
Wondering if we go deeper. Yeah, that's a good question.
Is there a way to use Roman to
that redshift? Somebody who's a lensing expert should say, but I thought that it was low. I mean, I didn't think depth was the limiting factor anymore.
I mean,
you tell me, Harry. You tell me.
I don't know.
I don't know.
I mean, presumably they're background sources, but the density may not be high enough. But
maybe a question for tomorrow. I think there's lensing tomorrow.
But you presumably want a mass map at the same redshift as our tomography map. So that would be redshift 2. I think you're running. I think it's a depth thing, right? Yeah. Well, if it's a depth thing, then we should be able to solve it.
I'm going to take chair's privilege and ask the last question. So I might have missed this with the kerfuffle at the beginning, but when is PFS going to be doing the observing, and how does the timing match?
That's the first thing I said. So we just got near-infrared commissioning spectra like a month ago. So we really are on track to start in 2024. We're supposed to start in 2024B officially. The Subaru community, for various reasons, is not interested in science validation time. So the GE survey will be spending our first year doing science validation, try to understand our selection and things like that. But we should have, our goal is to have at least 2,000 12-hour super deep continuum spectra in the first year. That's what we're going to go for. So everybody, think happy thoughts for PFS.
That's exciting times. All right. Join me in thanking all of our speakers again, both online and in person. Do the organizers need to say anything before lunch, or should we just go to lunch? I will
briefly say something about the discussion groups. So there are new Slack channels with the 6-7 topics that we discussed yesterday. Please put your notes so that the people online can see what the discussions were in person, and we can combine them for a successful summary session on Friday. Thank you.